Professor Davis with you again as we finish up Chapter 7. Measures of variation is Section 7.4. Well, in the previous section, we talked about measures of centrality, and these were numbers associated with the typical data item, and as the name implies, near the center of the data. But now, that only tells part of the story. With measures of dispersion, we're concerned about numbers that describe how data is spread out. Is it all clustered together, or is it spread out all over the place? So in order to compute these measures of dispersion, these measures of variation that we'll talk about in section 7.4, the data must be quantitative. It has to be numerical. So let's talk about a couple of these measures. The first one is very simple. It's called the range. We can say for a sample of data, a set of sample data, the range is given by the difference between the maximum and minimum data values. Now, as you can imagine, since we use these max and mins, just like with the mid-range, the range is susceptible to outliers, so we have to be cognizant of that. So let's just do an example and make sure we can compute the range. For an area of selected major bodies of water on the Atlantic coast region of the U.S., we have the area in square miles of those bodies of water. Let's compute the range of the data and interpret. All right, so I guess it looks like it's pretty simple here. We'll just take the maximum data value, 2,747 miles, and then subtract the smallest data item that we see, 492 square miles. So we'll get 2,255. All right. So there's our range computed. Let's go ahead and interpret that now. So this means that the range of the selected major bodies of water in the Atlantic coast region of the U.S. is 2,255 square miles. So that's pretty easy. And as we said, the disadvantage of using the range is that it is susceptible to outliers. So let's go to the next measure of dispersion, the next measure of variation, which next to the sample mean is certainly the most important measure in all of statistics, the sample standard deviation. We can say that given a sample of n data items, n being the sample size, the sample standard deviation, we'll just denote that with the lowercase letter s, it's given by, well, here's the formula for it. It looks imposing, but it's really not. Let's take a look at it here. What we want to do to compute the sample standard deviation is to take each data item x, subtract it from the mean, so we know, think of the number line. This would give us a distance that each data item lies away from the mean. Some would be to the left of the mean, some would be to the right. So to take care of those negative and positive values, we'll square those differences and then add them up. And then we'll divide by the sample size. We'll divide by the sample size minus 1. I'll talk about why that is in a minute. Now remember, we squared those differences, so now we'll just take the square root to unsquare them, so to speak. Now, if the population is regarded, if the data is regarded as a population of big N data items, then we can compute the population parameter, sigma, the population standard deviation, and to get that, notice the formula is different in that we take, it's not only the notation, we take each data item minus the population mean, remember we said that was mu, the Greek letter mu, square those differences, but now we're simply dividing by the population size n. So I guess the natural question is, why are these two formulas different? Well, usually we want the sample to mimic the population as best we can in terms of dispersion. If we collect a sample, usually that dispersion is a little bit smaller. So if we take the sample size and subtract 1, we make the denominator a little bit smaller. That makes this number a little bit bigger and better reflects what the variation of the data is. So we have to, now you can see this formula is quite complicated. You don't want to do this by hand, so we'll use our calculator to help us. So let's try an example here. Here's that same data we were looking at. Let's compute the sample standard deviation of it and interpret the solution. All right, so let me grab my calculator, and we'll do what we did back in the previous section. We'll enter our data into the stat editor. So we'll hit the stat button and click on number 1 for edit. And if you already have data in there, you probably do. Here's how you clear it out. Just hit the up arrow key to highlight L1, hit the clear button, and then hit enter. And that'll clear out the data for you. All right? So I'll go ahead and enter this sample data. $598, and our last one is $492. There we go. And now let's go ahead and do what we did before. Hit Stat, go over to the Calc menu, and select one variable stats. And then if we hit the Enter key, notice if we look right here, it says SX, that is our sample standard deviation. So, what does it look like? It's there. It's 870.6 if we want to round that to one decimal place. All right. So notice, by the way, we're also given the sample size of 6. Now, I'm also here, if I scroll down, that's what this down arrow means. It means there's more stuff. We get the minimum value, the median, and the maximum value. So when you're doing your homework, take advantage of that editor to do those kind of things. All right, so let's go ahead and interpret our solution here. We hit Stat and Edit, entered the sample data, then hit the Stat button again, went to the Calc menu, and selected one variable stats. There's our output, and so we can interpret the solution by saying we see that the sample standard deviation is given by 870.6 square miles. All right, so let's take a look at an application of the standard deviation that goes back to something we talked about at the end of the previous section. The idea of skewness. And this is a measure invented by Karl Pearson, the famous British statistician. And it's called the Pearson skewness coefficient. And we'll just write SK for skewness. And here's the formula for it. Here's what we do. We take the sample mean, subtract the median, divide by, take the sample mean, subtract the median, multiply that difference by 3, and then divide by the sample standard deviation. All right? And this will give us an idea of the skewness without having to look at the histogram or even the frequency distribution. So here's how we can interpret the Pearson skewness coefficient. If the Pearson skewness coefficient is positive, then the distribution is skewed left. Conversely, if the Pearson skewness coefficient is a positive number, then the distribution is skewed right. Negative skewed left, positive skewed right. If it's about or close to 0, then the distribution would be symmetric. And we saw that factor of 3 in the numerator. The values of the Pearson skewness coefficient typically range from -3 to 3. It's quite rare if it's any number outside that interval. So let's go ahead and try to compute one of these Pearson skewness coefficients and interpret the meaning. The ages of U.S. females in 1990 had a mean of 36.1 years and a median age of 34 years with a standard deviation of 22.9 years. Determine the Pearson skewness coefficient and interpret the result. All right, so let's go ahead and do that. Grab my calculator here and clear this other stuff off. So we'll take 3, and then we'll multiply it by the sample mean. That was 36.1. Then subtract the mean. That was 34 years of age. And now we'll go ahead and divide by this sample standard deviation of 22.9. Go ahead and hit enter. And what do we get there? 0.28 or so, rounding to 2 decimal places. All right, so let's go ahead and verify that work. So there's our calculation for the Pearson skewness coefficient. And notice here, the number is very close to 0, isn't it? Right? 0.28. So since it's positive, it's skewed to the right, but it's just very slightly skewed to the right. All right? So that is how we can use the Pearson skewness coefficient in an application. And that takes care of measures of variation.